Okay, our second speaker of today is Lavinia Heisenberg. She will tell us about gravity with non-metricity. Please, Lavinia.
Yes, thank you. Thank you very much for having me. Yes, so I will talk about gravity with non-metricity in case you have seen such a talk of me. Apologies if this is some sort of a repetition, but I would like to be rather pedagogical and introduce all the needed tools or variables in order to describe gravity in terms of non-metricity rather than curvature. Okay, so thanks to Einstein, we have actually already a theory of gravity since 1915 or whatsoever, but maybe there are different ways of representing the same theory with a different mindset or with a different formulation or interpretation. So Einstein actually went on and postulated that gravity is a property of space-time and that gravity is geometry. And compared to the Newtonian interpretation of gravity, this is a rather very radical change. Instead of assuming that there is a force between two objects, it's actually due to the property, due to the geometry of your space-time. So in this cartoon kind of picture, imagine you have a completely flat space-time and now you put Earth on it. Due to the mass of this object, the space-time gets curved. And if you have another object, like for example, moon or whatsoever, it will feel the gravitational attraction of this bigger object due to this curved space-time. And then any other test particle will follow the curvature given by this space-time. So general relativity exactly equals to the interpretation of curvature of space-time. So now I will put a question into the room, namely, can we actually instead try to describe gravity as a gauge theory in a very similar way as we try to describe, for example, the Young-Mills theories as gauge theories? And the answer to this question is a big yes. Yes, we can. But for that, we would need to introduce a more general geometrical setup than what we have in the standard formulation of general relativity à la Einstein. So let's do that. Let's introduce the necessary geometrical framework that will allow us to describe gravity as a gauge theory. So let's consider a manifold M. So a manifold is nothing else but a topological space that resembles the Euclidean space near each point, for example, the sphere and the torus. So at each point near this point, this space resembles the Euclidean space. For example, Earth is such a simple manifold. And then you can now put points on this manifold. For example, these are the coordinates of where Zurich is. So once you have your manifold, you can now put points on your manifold. You can do more. So you can now, instead of just putting a point in this manifold at this point X, you can also attach tangent spaces here. This thing here at each point X. And in this way, you get a tangent space. And this is basically all the real vector space that contains the possible direction in which you can tangentially pass through this point X. So we have manifold, and at each point, we can attach a tangent space. We can also now introduce coordinates in our manifold. They will be useful to do certain transformations. So, for example, this will allow us to define tensors that live on this manifold. Here is one example of such a tensor that lives on our manifold, and it's basically given by the way how this tensor transforms under the change of coordinates. So tensors are always associated to a transformation law, and in this case is the change of coordinates. So this will allow me then to introduce scalars, vectors, tensors on this manifold. Just a simple example, for example, a scalar field that basically doesn't change under coordinate transformation. This could be, for example, the temperature on Earth. You can also introduce vector fields that live on this manifold. They transform in this specific way here under change of coordinates. It could be, for example, at each point on Earth, the wind direction could be such a field. Now, as next, what you would like to do after you have introduced fields and tensors living on this manifold is somehow to be able to compare them. Imagine you have one point where you have a vector at point Q, and then you have another vector at point P. Can you like subtract them? Can you just compare them in a physical sense? And so vectors from different spaces in general cannot be compared. So if you have one vector at point Q and you have another vector at point P, in principle, they cannot be just naively comparable. So even though they are not equal, they are isomorphic to each other. And you can use that in order to compare the vectors. And this is the way how you do it. So imagine in my manifold, I now also introduce a curve, here this gamma curve, that passes through this point X. And then there's a specific tangent vector here that I am pointing it here, that is basically tangential to my curve at point X. And now I could take a vector field or one field that lives on my manifold and ask the question, how does this vector field psi changes when I move it along this tangent vector? And this is what this operator doing it. So it takes your field, in this case is a vector field, it takes your field that lives on the manifold and it varies along this tangent vector v in order to move it along this curve gamma. And when you do that, you can write it out. So it's the derivative acting on your vector field decomposed in your basis elements, these E alphas. And then you basically have to perform this derivative once on the vector field components and once on the basis elements themselves. And here you can already recognize this is where the connection pops up. So basically, if you have here at point X, your basis elements attached to that, and now you change this basis element along your tangent vector, this is exactly what your connection is giving you. And you probably recognize that you get your covariant derivative out of that. So if you want to be able to compare fields like vector fields that live at different points on your manifold, you necessarily need the connection. So the covariant derivative of a vector field, for example, here is given by the partial derivative plus the connection. And here, please be careful. So this connection is a completely arbitrary general connection that I constructed by how this basis elements changes when I move along my tangent vectors, and it has nothing to do with the Christoffel symbols. I didn't even introduce the metric yet, so that you are not even allowed to talk about Christoffel symbols. Now, then, since you have the covariant derivative, you can manipulate it, you can build certain commutators and act them on your fields that live on this manifold. For example, if you consider the commutator of your covariant derivatives and act it on a scalar field, is this 0 or not? Of course, in standard general relativity, this would be 0, but if you have this general manifold with this general connection, you can actually explicitly compute this commutator. Then you will have the partial derivatives coming in and then the connection part. And you see that this commutator acting on the scalar field is exactly proportional to the antisymmetric part of the connection. And this antisymmetric part is nothing else but the torsion tensor. So this commutator acting on the scalar field is only zero if your manifold had a vanishing torsion. But in general, in the most general setup that you might think, the torsion will be present. You can do the same thing, basically compute the commutator of this covariant derivative, but acted on a vector field. And in this way, you see that now the Riemann tensor pops up, the curvature that is given in terms of your connection in this very specific way. And then you also obtain the torsion again. If you now take this commutator and act it on higher order tensors with 2, 3, 4 indices, you don't obtain any new tensors arising. It's going to be always a repetition of the Riemann tensor and the torsion tensor. And then you can build different contractions of the Riemann tensor. You probably know this is, for example, the Ricci tensor. But since you have a very general setup, geometrical setup, depending on which indices you contract of the Riemann tensor, you will get different type of tensors, like this homothetic tensor and the co-Ricci tensor. Actually, the co-Ricci tensor, you were not even allowed to write it because I didn't even introduce the metric. But if you had introduced the metric, you could also have this independent contraction. Anyway, so we have seen that the curvature arises very naturally when you take your covariant vector and you apply the commutator of your covariant vector to vector fields. So what does the curvature do in your manifold? Imagine you have a vector with a certain direction, and if you move it now along a closed curve and you come back to where you started, then the direction of the vector field will change if you have a non-zero curvature. So basically, curvature is nothing else but a measure how vector fields change their directions in the manifold that they live. So we can also add vectors together. If you had just a flat manifold, if you add these two vectors together, you get a nice parallelogram. But if you have a general manifold, general geometrical framework, then this parallelogram doesn't necessarily close, and this is what the torsion tensor basically does. Okay, so summarizing, what we did is we considered a manifold, and then we said on this manifold, we can put points on that manifold. At each point, we can attach tangent spaces, and then we can introduce coordinates, and basically based on how fields change under this coordinates, we have introduced fields living on this manifold. And now when we also introduced the covariant derivative and acted on these fields, we have seen that there is this Riemann tensor arising that depends on the connection, and the torsion tensor arises that depends on the connection. So Riemann and tensor are geometrical quantities that only depend on the connection. So they have basically nothing to do with the metric as you are used to in the standard formulation of general relativity. So far we have only introduced the connection, and its field strength, we have seen that it has introduced the curvature and torsion, and there's no metric yet. But in order to do more, I really need to introduce the metric. So as next, I would need to introduce the metric on this manifold. It basically takes two vectors on the tangent spaces and gives you a real number. So it's a bilinear true form, and it's symmetric, and it is non-degenerate. So its determinant should be not vanishing. And it transforms in this very specific way under change of coordinates. Okay, so the square root of minus g has tensorial density of weight minus 1. This is the reason why we use it always in our Lagrangians. Okay, now since we have our metric, this allows us to compute lengths on our manifold in this way. We can compute areas on our manifold. We can basically build triangles, and we can follow the motion of test particles, the geodesic equation. And as you can see in this geodesic equation, it's only the Christoffel symbol that appears here, which is completely given in terms of the metric. So then with this metric now, I'm able to do more interesting stuff on the manifold. Since I have the metric, there is actually yet a third important geometrical object that I can introduce, which is the non-metricity tensor. And it's the covariant derivative acting on the metric. So it's the definition. But this is the covariant derivative with respect to this general connection and not with respect to the Christoffel symbol. And what I could do, I could basically now take vectors and see if I had a manifold that has a non-vanishing non-metricity, what happens with my vectors? And one immediately observes that the lengths of vectors change if you have a non-vanishing non-metricity in your manifold. Now you can basically take this definition of the non-metricity, and you can do all the permutations of the coefficients, and then sum these two equations and subtract the third one, and then you can solve it for the connection. And when you do that, you immediately observe that the connection is given by one piece, which is exactly the Christoffel symbols that you are very familiar with from standard general relativity. But then you have this formation tensor given by non-metricity, and then you have this contortion tensor, which is given in terms of torsion. So a general connection in a generic manifold will have these three pieces. So the complete properties or the complete setup of your manifold is such that your manifold has a metric and then a completely independent general connection. From this connection, you can directly obtain the Riemann tensor and the torsion tensor. We have seen that Riemann and torsion only depends on your connection. And from both the metric and the connection, you can then obtain the non-metricity tensor. So these are these three important geometrical tensors that your general manifold can have. And based on those tensors, you can then describe your gravity theory. So in the remaining, I will focus on this one option here, saying that my manifold is based on non-metricity. So, and then I will impose flatness. I will impose the teleparallelism condition. So I have to impose that the Riemann tensor for this general connection vanishes identically. And this has huge implications because this condition fixes your connection to be a pure general linear group, and it fixes your connection in this very specific way. So this gamma is not general anymore, but it has to satisfy this condition. And so it's given here in this very specific form, where this lambda represents basically the elements of the general linear group. Okay, so let me introduce coincident general relativity that is basically based on non-metricity with this teleparallelism condition, namely that curvature vanishes. Okay, you have a manifold based on non-metricity, as I said. Your fundamental objects are both the metric and the connection. And we have seen this connection has this important piece, that is formation tensor. You live in a space-time which is curvature-free. This was our teleparallelism condition. But I will also further impose that also torsion vanishes. So the only geometrical object that remains is the non-metricity. Okay, so we have seen this teleparallelism condition, namely imposing that the Riemann tensor vanishes, restricts the form of your connection in this very specific form. And if we go further and impose that also torsion vanishes, this lambda basically becomes then pure diffs here, given by this size, so restricts this even further. And then your gamma is simply given here by this form. So one very important particular property then is that the connection, for example, could be set to 0 by means of a gauge choice. So when you choose disk size in a very specific way, you can make that your connection vanishes everywhere. And this is a very specific gauge choice, but you don't have to choose this gauge. Okay, so we have our connection and we have our metric, and from that we built this non-metricity tensor, and now we would like to write down an action, a Lagrangian. And as you can see, this tensor has 3 indices, so we cannot contract it to build a scalar quantity at the linear order. We have to go to quadratic order. But because it's symmetric in the mu indices, I will have 5 independent contractions at the quadratic order. And then, so I have here these 5 independent contractions of the non-metricity tensor. And then with Lagrange multipliers, I make sure that curvature vanishes and torsion vanishes. And only if you choose these coefficients in this independent contractions in this very specific way, you obtain an equivalent theory to general relativity, which only has 2 propagating physical degrees of freedom. And these contractions with these coefficients look then in this very specific way. Okay, so in this coincident general relativity, basically, instead of having, let's say, this geometrical interpretation that gravity is due to curvature of space-time, now we have this interpretation that gravity is due to changes of length. So you have completely flat space-time, and you have your object now. You have a second object, and you have test particles moving around. It will follow the same geodesic equation. It's just now is not due to the curvature of space-time, but due to the change of this tangent vector of your test particle. And it just represents a different interpretation of gravity. Okay, so we have seen that you can take your connection and you can decompose it in these 3 pieces, the Christoffel symbol, then the torsion part, and the non-metricity part. And we can plug this into our expression for the Riemann tensor. And when you do that, then you will definitely have the standard Riemann tensor associated to the Levi-Civita part. And then you have torsion terms, non-metricity terms, and some derivatives acting on them. Okay. So when we postulate that the torsion vanishes, of course, in this expression, we then get rid of all the torsion terms. And then and then we can even contract the indices and compute the Ricci scalar. And when you do that, you see that the Ricci scalar of your general connection is given by the standard Ricci scalar of the metric of the Levi-Civita part, plus this curly bolt and Q scalar, which is the non-metricity scalar, which explicitly is exactly the very specific contractions, the quadratic contractions with the coefficient C's chosen such that it really corresponds to general relativity. And now if we impose that curvature vanishes, so if this thing here vanishes, you see that the standard Ricci scalar of your metric of the Levi-Civita corresponds exactly to your non-metricity scalar plus some boundary terms with some total derivatives. Okay, so you have this standard action of general relativity, the Einstein-Hilbert action. And then the equivalent description would be this standard, the symmetric teleparallel equivalent of general relativity, now based on non-metricity, and given in terms of this quadratic contractions with this C coefficients chosen in this very specific way I have shown. And these two Lagrangians are exactly the same up to some total derivatives, so they differ by boundary terms. So you can then also compute the field equations of this equivalent theory. You have to now vary with respect to the metric and with respect to the connection because they represent independent fields. Then you obtain these equations here with this P alpha mu nu given in this very specific form here. And similarly, Q is given here by this term. Essentially, what you have here from the metric variation is equivalent to the Einstein tensor. And what you get from the connection equation is actually an identity equation, kind of like a constraint equation. And as you can see, the equations of motion are identical to Einstein's field equations. Only at the level of the action, they differ by boundary terms. Okay, so this was coincident general relativity, and one very particular property that I mentioned was that you can choose the coincident gauge in which you can make that the connection vanishes. And if you do that, then you immediately see that your quadratic non-metricity scalar with these coefficients chosen such that you obtain GR is exactly equivalent to the Christoffel squared part of your standard Einstein-Hilbert action. So the terms that are where you usually have a partial derivative acting on the Christoffel symbol are not present here. And this has huge implication because usually second derivatives acting on the metric causes quite a few trouble, which is something that we don't have in our other standard theories of the standard model, for example. But in the standard formulation of general relativity, we have this second derivatives acting on the metric, and that causes problems. For example, if you have a compact manifold and you perform your variational principle, then the variational principle is not well posed, and you have to introduce this Gibbons-Hawking your boundary term in order to be able to vary your action. There's actually also a more direct contact with the particle description of general relativity within this non-metricity formulation. And also this improved action principle can make differences in consideration of energetics, thermodynamics, and quantum theory. So if you want to compute the entropy of a black hole, or if you want to quantize your theory, due to these differences of boundary terms, and due to the fact that you don't have second derivatives acting on your metric, will have implications. Okay, so this was coincident general relativity. So if you were kind of like confused that on one hand we have GR where spacetime is curved, and now you have this symmetric teleparallel equivalent of GR where spacetime is flat. How can this be true? now you understand that the difference comes really because here it's the Riemann tensor associated to the Christoffel symbol, so to the metric that is not zero. And here in this formulation is the general Riemann tensor of the arbitrary connection that is zero. Okay, so we understand now this comparison better, hopefully. So before I move on, this was now coincident general relativity. Are there any questions? Doesn't seem to be the case.
Yeah, no.
Okay.
But so you're saying now you don't need the Gibbons-Hawking term, but before that you discarded the boundary term, this derivative of Q alpha minus Q alpha something. So shouldn't you keep it if you would have a compact manifold?
No, you don't have to keep it. That's the whole point, right? Where did I write this? No, I don't have it here. So that's the whole difference, right? If you had standard general relativity and you had a compact manifold.
Sorry, can I ask a question?
I was answering the question that was just.
I thought you were something. Yeah, please. Yeah.
May I first maybe reply to the previous
Yeah,
question?
please.
And
Yeah,
have a
there's
second one.
some confusion. Sorry.
Yeah. So if you had standard general relativity and you had only this piece, right? This is your standard general relativity. Because it has second derivative in here, then you would need to introduce the Gibbons-Hawking-York boundary term. But now in non-metricity formulation, which is basically this piece, because you don't have second derivatives on the metric, you don't need to introduce any boundary term. This d alpha applied on the q alpha, this is only if you ask me to compare it to your standard Einstein-Hilbert action. This is just for comparison reasons. But if I do real computations, I don't need this boundary term. Everything covariantly is included in this Q. Okay? So just to remove this confusion.
Right. So you're saying that I just formulate a theory without this term, even though it only equivalent to GR for compact manifolds if I would keep it, right?
So yeah. So I what I said is in my Lagrangian there's only this Q, and this Q Lagrangian now differs to your standard Einstein-Hilbert by this boundary term, but I never put this boundary term in my Lagrangian. It's only for comparisons if you want to compare it. At the level of the equations of motion, they're completely equivalent, right? It means in terms of dynamics, they're going to give rise to the same equations of motion, to the same dynamics. But at the level of the action, if you insist on comparing them, you see that they differ by this boundary term. But if I compute like the entropy of my black hole, or if I want to quantize it, I just use my Q Lagrangian, which doesn't have second derivative acting on the metric.
Thank you.
We have a second question now.
Yes.
In the case you have no metricity, how do you introduce fermions?
So the case you don't have or you have?
In the case in which you have.
Yes. So yeah, in the case of you have non-metricity, very natural question would be also how do the matter fields behave? Not only fermions, but also bosons. And this was exactly what I wanted to talk as next. But are there other questions about?
One more question.
Yes.
Hi, this is Hans Mühlen. In your coincident gauge, you got a very simple form for your action, but isn't that exactly the Einstein version of the GR action, the one that down below on the right-hand side?
Yes.
That's the one he published in 1915. Isn't this a very complicated way of deriving something that you already had in 1915?
Uh, sure. I mean, in the coincident gauge, this coincides with what Einstein had, but this is not completely fully covariant theory, right? And
Exactly,
exactly. The price to pay for this was you had to add this partial derivative acting on the Christoffel symbols in order to make it to the Ricci scalar, and which has introduced the second derivatives of the metric. If you want, this non-metricity, due to your general geometrical properties, allows you a covariant description of your gravity theory where you don't run into these problems of having second derivatives acting on the metric.
Yeah, I mean, this Einstein's version of the action, which differs from Hilbert's version, which we use today, is precisely that you take away the double derivatives. They are just
yes. But you see, I mean, if you follow Einstein's formulation, you would say, okay, my manifold is given by metric and the Christoffel symbols, which is completely determined by my metric. And now I use the curvature in order to build scalar quantities, and this gives you the Ricci scalar. This would be the covariant theory. But because his first attempt was actually not a covariant theory, this is why he mistakenly first had this Lagrangian. And this Lagrangian doesn't have the property that he wanted to have, that namely that gravity should be a fully covariant theory. And now, instead of following from the very beginning this assumption that your manifold consists only on the metric and that your connection is basically completely trivial given by the Christoffel symbols, basically by the metric, you allow a more general setup, and then you end up with a different covariant theory, which doesn't have this problem of second derivatives. I don't know if this answers the question. Okay, seems to be the case. Then I will now move on and ask the question. This was the pure gravity description, but we know that we don't just have the gravity sector, but we also have the matter sector. So how do the matter fields behave in this setup? Okay, so now the coupling of matter field. Of course, in standard formulation of general relativity a la Einstein, this formulation has also a very important principle, which is the minimal coupling principle, which basically says that if you have any fields, any matter fields, imagine you have some gauge fields, this A field here, that lives on Minkowski spacetime. If you promote that now to curve spacetime, living in general relativity, you have to promote the Minkowski to a general metric, and then the partial derivative to covariant derivative with respect to the Christoffel symbols. And the minimal coupling principle says basically that all the fields have to couple to the metric, to its determinant, to the inverse of the metric, basically the square root of minus g, but never to derivatives acting on the metric. So this is the minimal coupling principle. So general relativity goes hand in hand with the minimal coupling principle, and only then you obtain the theory of general relativity. So I didn't even talk about this teleparallel equivalent of GR, which is based on torsion. Basically, if you try to apply this minimal coupling procedure, you see that it doesn't work. The bosons, the photons, whatever, non-minimally coupled to the torsion, and this would break the equivalence to general relativity. But if you have coincident general relativity with the non-metricity, and now you apply the minimal coupling principle to this case, you see immediately that the minimal coupling is preserved, and that your photons follow exactly the same geodesic equations, so they have exactly the same field equations, and the non-metricity completely drops out. And now if you have fermions, if you introduce fermions, the story is basically the same, that torsion really insists on coupling non-minimally to your fermions. And in this way, you would also get something which is not equivalent to general relativity. But if you now assume that your theory is given by the non-metricity equivalent theory of general relativity, then the fermions, again, do not couple to the non-metricity, and they have exactly the same equations of motion as in standard general relativity. So if you write down your action for your Dirac fermions, and you write the covariant derivative with respect to this general connection, you see that the non-metricity piece completely drops out due to the symmetries, and then you get exactly the same Dirac Lagrangian as in standard general relativity. So concerning bosons or fermions, then the equivalent description between general relativity consists only if you have non-metricity and if you impose that torsion vanishes completely. So as soon as you have torsion, then things becomes complicated. Your matter field insists on coupling on your torsion, and then you would either ad hoc by hand make these couplings zero, or if you don't want this ad hoc vanishing of such couplings, you need to remove torsion from your manifold. So this was concerning the manifold, the matter field coupling. Does this answer your question? There was someone asking about fermions.
Well, it is well known that in order to couple fermions to connections, the non-metricity has to vanish.
No, I'm making you stated
unless you take two different connections for fermions. So, for example, if you take for the fermions, you take the Levi-Civita connection, and for
no,
vectors,
I'm not taking any different connection, right? My statement is I have my gravity, which is written in terms of this Q scalar, right? This non-metricity, quadratic non-metricity. And then I have my Dirac Lagrangian, where I have the covariant derivative, again, with respect to this general connection. And I am saying that this non-metricity from that Lagrangian drops automatically. I don't need to impose that non-metricity vanishes. It means that the fermions have exactly the same equations of motion as in standard general relativity. I am not doing any ad hoc piece of, Christoffel enters only in that piece of my action in the matter field, and my other general connection enters only in the gravity sector of my Lagrangian. This is what I would call ad hoc, and this is something that you would need to do if you had torsion. But I am saying that it's exactly the opposite, that if you have non-metricity, all these terms, all these couplings completely drop out, and you have just the standard minimal coupling as in standard general relativity.
Oh, well, so if you open, for example, it's known in supergravity that this is the case, that non-metricity cannot appear in the covariant derivative of fermions.
It depends on very specific. It depends on very specific assumption of your supergravity. So, if I am telling you, if you have a standard Dirac fermions, the standard Lagrangian, right, with the psi bar, the derivative, and this derivative has now the general connection gamma, which
you have to introduce tetrads in that case, tetrads and spin connection.
You can do it in any language you want. I mean,
you really
I'm making this statement fully covariantly without fixing any frame or any tetrads.
Well, for fermions, you really have to introduce tetrads and spin connection.
Sure. I mean, you can do this. You can basically take your fermions and you can say, okay, you have these frames and you have the spin connection associated in that frame bundle, and you do all the computation in there. But I am telling you that you can exactly do the same computation covariantly, fully covariantly, using your covariant derivative without using any frames, any tetrads, or whatsoever. And there the non-metricity appears in that connection. I didn't put it to 0, but nevertheless, it has no effect because of the symmetries. It basically drops out. And if you now do the same thing in terms of the tetras, you would get exactly the same result. But since you are talking in terms of supergravity, maybe there are other certain assumptions or stuff that is needed that has a very particularity that is not within general relativity. Here I am talking, if you have general relativity and you have your standard Dirac Lagrangian for the fermions, your minimal coupling is preserved.
What is the standard Dirac Lagrangian for fermions? Sorry, the covariant derivative is equal to. So there's a derivative plus. How do you couple fermions to gravity?
Yes, this.
Do you have a slide, or do you have a slide?
This covariant derivative is the partial derivative plus the general connection gamma, which is given in terms of this non-metricity, this formation tensor L that I had.
Yeah, but how does this apply to fermions? Fermions
Anyways, you can have a look at this paper. There is all the details given, all the Lagrangian and the equations of motion.
We have another question on Zoom. So
yes.
Yeah, hello everyone. My name is Jens. Lavinia, good to see you. I wanted to add a comment on this. So there is a 1995 physics report on fermions and non-metricity by Neyman and Hale and collaborators.
Mm-hmm.
I think what they say is that because the holonomy in a non-metric theory with non-metricity is in general a general linear transformation, it sort of like affects the way that you can define a local Clifford algebra. And it depends on how this Clifford algebra changes from point to point. And I think that's the reason that if you want to define fermions sort of like ab initio in this kind of setting, you have to do something else. So they construct it in their paper. But I guess that's also like a point of debate, because if you just say, well, I would just want to minimally couple my Dirac equation to non-metricity, which is I think what you are doing, then this is completely, like you said, of course, self-contained, right?
Exactly. And I mean, I had a bunch of email exchanges with Hal, and this is the whole difference. I am saying that the minimal coupling is for me a fundamental principle, which is also the fundamental principle in the standard formulation of general relativity. And if I assume that, and I have my standard Lagrangians of my matter field, with just the covariant derivative now being the general one, then I see that the fermions behave exactly in the same way. So I am following explicitly the minimal coupling principle.
If I may, I was going to ask you something about coupling of matter, since it's on the slide right now. So you mentioned in the beginning that your motivation for this was the analogy to gauge theory, right?
Mm-hmm.
And in gauge theory, for each local gauge redundancy, you typically get a gauge potential. And each one of these also couples uniquely to some sort of matter current. So, for example, in U1 electrodynamics, you have just the U1 current on the right-hand side of the Maxwell equations. And in this case, since you set the curvature to 0, the torsion to 0, you showed your two field equations. What are the right-hand sides? What are the matter currents that couple, like in the language of gauge theory? Just want to expand on that a little bit. Thanks.
Yeah. So, I mean, in terms of your right-hand side, basically, you need something which represents basically the stress energy tensor, right? The T mu. And now the question is, how do you get this T mu? And if you have your action of your matter field, and you follow this minimal coupling principle, then you have your metric, and you vary now your action with respect to your metric. And this would give you the right-hand side of your Einstein's field equations, what the matter fields represent. So in terms of gauge fields, if you want, or in terms of a gauge theory, the way how we now achieved to write gravity as a gauge theory was due to our connection and imposing the vanishing of the Riemann tensor, the general Riemann tensor. And this made that our connection became the connection of the general linear group. And basically, the connection represents your gauge fields associated to translations. And now, if you also impose that torsion vanishes, we have seen that these gauge fields become then pure diffs, disk size. And now you have basically disk size, which represent your complete, I mean, your gauge mode, so to say, your diffs, but they would not directly couple to the matter fields. They are unphysical gauge modes. So this is like if you would say in standard electromagnetism, your temporal component and your longitudinal component of your vector field, they don't couple to the matter field. They are just redundant gauge modes that completely disappears from your equations of motion, either after you fix a very specific gauge or you try to deal with it in a gauge invariant variables.
Yeah,
And
Lavinia,
here-
you have 10 minutes, just to remind you.
Yes, okay. I have 10 minutes. Maybe I will just shortly. So if you want to have more details, you can have a look at this review article. But then I will now shortly try to move away a little bit from general relativity. The reason is the following. Now we try to model our universe. We describe our universe based on these 5 fundamental pillars: general relativity, dark matter, dark energy, the inflaton field, and then the cosmological principle that the universe is homogeneous and isotropic. And then your Friedmann equations are much, much, much simpler than the compared very complicated Einstein's field equations. But then there are these troubles, as we know. I mean, how do we, for example, get inflation from quantum fluctuations? Then we have the indication that the majority of energy and matter form is actually not in form of ordinary matter. There seem to be some observational tensions, like the H0 tension. Then we don't really have a quantum theory of gravity. And there are singularities that pops up here and there. So you are basically forced to extend your gravity theory either fully classically or quantum. But in both cases, you have to really go beyond general relativity. If you do quantum, maybe this is string theory or whatever favorite quantum theory you have, and you typically introduce new degrees of freedom. And also classically, as soon as you move away from general relativity, you start adding up new degrees of freedom in terms of additional scalar vector or whatever degrees of freedom, unless you are willing to break certain symmetries like Lorentz symmetry and so on. So here is a very specific geometrical extension of GR. Imagine we take coincident GR with this quadratic non-metricity scalar with these coefficients very specifically chosen so that you have GR. You can promote that now to a general function f of q. In the same way as you have f of r, if you had curvature, you can also have f of q type of theories. So there has been quite a few activities in the literature. If you want to know more about it, feel free to have a look at the recent review here that I'm putting. I will only just quickly introduce it. So you have now this Lagrangian basically where you have now f of q, a general function of this non-metricity scalar, your equations of motion with respect to metric and with respect to torsion, with respect to connection, sorry, change in this very specific way. And then you have, in this way, modified your dynamics, and you have added additional degrees of freedom since it's not general relativity anymore. So you can do, for example, cosmology with it. Here is a very specific example with this specific ansatz, with a power law ansatz alpha here. Your basically cosmological equations, the Friedmann equations, modify in a very specific way. And now depending on what this alpha is, you can have either modifications in the early universe, which would be important for inflationary physics, or you can have modifications in the late universe if you choose alpha in this specific way. And this would be relevant for dark energy applications. It has also implications for black hole physics. If you have now a different theory of gravity instead of general relativity, simply because you have now connection, not just the metric. Now you have to impose the same conditions as we do in standard general relativity in order to get the black hole solutions, namely stationary and spherically symmetric setups. But on top of that, we also impose that you have torsion-free and flat conditions. And the coincident gauge in this case does not have these properties. So if you want to study black holes, it's not allowed to choose the coincident gauge. It's basically not compatible with these four conditions in order to get a spherically symmetric solution. And there are two parameterization that satisfies these conditions. First, you do the same thing and you find the metric that satisfies these conditions. It's basically essentially the same thing as in general relativity. You can use diffeomorphisms in order to bring it in this diagonal form that we are used to. Now you do the same thing for the connection, which has more components than the 10 components in the metric. And you impose your conditions, the torsion vanishes, this leaves 40. Then you impose symmetry conditions, like the spherical symmetry. And then you end up having just 12 components remaining. And the metric field equations have this very specific form here. And these are then the connection field equations, where you have only two non-vanishing equations of motion. And essentially, this equation of motion coming from the variation of the metric already imposes very strong conditions. And it basically allows two different parameterization of your connection, or two different solutions of your connection. The first one just gives GR solutions, like standard black hole. So there's no beyond general relativity solution. And only in the second one, you can actually obtain also beyond GR solutions. And in this case, you can, for example, have something like a connection here as an additional new physics on top of your standard Schwarzschild black hole. Okay, so if you want to, as I said, know more about the topic of this talk, feel free to have a look at this review article. Okay, I stop here. Thank you very much for your attention. And if you have more questions, yeah, let me know.
We have a question. Zoom.
Hey, thanks. Thanks for the talks, Lavinia. I have a question concerning the quantization. Have you looked to, like, is there anything that we should expect to be different when you do canonical quantization of this non-metricity theory, as opposed to normal canonical quantization of GR?
Yes, so unfortunately, I cannot answer it 100% because no one has looked at it yet. because you have to now, when you quantize it, you have to you have to introduce not just the metric but also the connection, and that makes that things are a little bit more complicated. But one naive expectation would be, as I was saying, that the difference to the standard Einstein-Hilbert action is this boundary term. Because of this difference in the boundary term at the level of the Lagrangian, I would naively expect differences in the quantization procedure. Of course, now it depends also from a very specific quantum gravity application that you are interested in. For example, if you come from loop quantum gravity, then the way how you do there with the, for example, the Ashtekar connection and all the variables that you build in there, they will then slightly change because you have now this piece in the connection that comes from the non-metricity. So no one ever has looked at it, but I would definitely expect huge differences. Yeah.
I was particularly puzzled, and maybe I didn't quite understand, but I thought that the connection would be or could be seen as pure gauge in this case.
So, of course, if you have just standard general relativity, the degrees of freedom in the connection at the end of the day is like just gauge modes, right? They don't introduce any new dynamical degrees of freedom. But if you want to work fully covariantly, then you need to introduce the connection. And for example, in loop quantum gravity calculations, these things are done covariantly, and but you could also say, okay, let me choose the coincident gauge, and then you get rid of the connection, and then you can try to build new ways of calculating this, the Hamiltonian, and you're constraining the Hamiltonian within this coincident gauge. So you have to choose, like, does your quantization rely on having covariant description or not?
Okay, thank you.
Yes. I was curious about what you suggested, that there could be changes to black hole entropy. And do you have anything on that to say?
Yeah, so actually, in terms of the end number, in terms of the end number of an entropy of a black hole, there is no difference.
Yeah.
But there is a huge radical difference in the way how you compute it. So in standard general relativity, when you compute the entropy, for example, using the path integral, you have to introduce the Gibbons-Hawking-York boundary term, and then another counter term to basically normalize your contribution, and you have basically GR plus Gibbons-Hawking term plus this additional counter term in order to really get your right number at the end for your entropy. And in the case of the non-metricity, you just get it directly from this Q scalar. You don't need to introduce your any boundary term or any counter term to renormalize it. It pops up, automatically through this covariant scalar. Now, why is this relevant? I mean, imagine your space-time had less isometries, like it didn't have the nice spherical symmetry of black hole, but symmetries explicitly would have broken. Then to guess the right counter terms and the right corner terms, the right normalization terms might become difficult. Whereas everything covariantly packed comes already here in the queue, and that's the huge difference. But in terms of, like, at the end, the number that you get is the same.
Yeah, the number is the same whether independently of the asymptotics of the unit, if it's ADS or flat or etc.
Yes.
Yeah.
Okay, thank you.
Okay, Lavinia, we do have more questions, but which we'll postpone to discussion session after the coffee break. So now we will go for coffee and we will meet at 11:45.
Sure, thanks.
Let's thank Lavinia.